Inbound to Blake. Steve takes a half-court shot.
We've all seen NBA stars make amazing buzzer beaters, but what exactly goes through the mind of a basketball all-star as he shoots a half-court shot? To look into this question, we decided to look at the physics of the shot. We can break down a basketball shot into two key topics. The first is the initial velocity, and the second is the angle above the horizon. These two components work together to make the perfect shot.
Takes a half-court shot.
To look into these two components further, we tried a few shots for ourselves. Let's dig deeper into this shot. Using Tracker, we were able to find that the initial velocity in the x direction was 7.8 meters per second, and the total time to reach the hoop was 1.334 seconds. We still need to find the initial velocity and the initial angle. To start off, we wrote down everything that we knew. The height of the basketball hoop is 3.05 meters. The height to the hoop was 10.4 meters. The height of initial release was 1.83 meters. The initial velocity in the x direction as found by Tracker was 7.8 meters per second, and the downward acceleration was 9.81 meters per second squared. To find the initial angle, we had to find the initial velocity in the y direction. To do this, we used the kinematic equation position final equals initial position plus initial velocity in the y direction times time plus 1/2 acceleration time squared. We plugged into the positions and vertical acceleration as well as the time that Tracker calculated for us. When solved, we found our initial velocity in the y direction to be 7.46 meters per second. We used the two velocity components to find our angle, being inverse tan of 7.46 over 7.8, which equaled 43.7 degrees. To find the initial velocity, we had to use our initial velocity in the x direction, 7.8 meters per second, over the cosine of our angle, 43.7 degrees. This gave us an initial velocity of 10.79 meters per second. We want to see how precise you need to be to make this basket. Therefore, we decreased the angle by 5 degrees and kept initial velocity the same. We're going to look to see how close the ball will come to the basket when it reaches a height of 10 feet. The change in angle changed both of our velocity components, as seen on the left. We used the same kinematic equation as seen earlier and plugged in our new vertical velocity, positions, and acceleration to find a new time of 1.16 seconds. Knowing that horizontal change in position is equal to the velocity in that direction times the time it takes, we calculated the distance to be 9.77 meters. This means that the ball would undershoot the basket by over 2 feet. Here we can see that the change in angle of only 5 degrees made the ball fall short just about 2 feet and 2 inches. After reviewing the precision it takes to make these half-court shots, let's reflect on the incredible skill that it takes to make them. During timeouts, the players aren't pulling out their calculators to find out the angle and velocity needed to make the shot. Instead, the decision is made in a split second by their physical instincts. When looking at the accuracy it takes to make such a shot, we can really appreciate the mastery needed to become a professional athlete. Whether it's basketball, football, soccer, or hockey, the amazing plays we see on SportsCenter are even more spectacular when analyzed using physics.